So welcome back to the Introduction to Data Structures course. We are in lecture 2, Complexity Analysis. So in the last lecture, we have stopped at the topic efficiency. So we have defined efficiency in terms of two aspects. One is time and one is space. So time is nothing but the running time of an algorithm, where we write an algorithm and we analyze how much time will be taken by each and every instruction that we have written. And space is another parameter to analyze the complexity, analyze the efficiency of an algorithm. So space is in terms of the memory that is being occupied by each and every instruction that we have written in the algorithm. So these are the two parameters based on which we can define the efficiency of a algorithm. So I have given some of the examples here. One is a library management system. The second one is a telephone dictionary organization. And the third one is a textbook glossary. So as we all know, in a library, the textbooks are actually organized in a particular fashion so that the retrieval process, that means finding out a particular textbook, will become much easier. For suppose if you imagine that a library, instead of being organized in a particular fashion, if let's say if it is organized in a random way, it takes a lot of time for the librarian to identify the book in a pile of books. So similarly, telephone dictionary, as we all know, the dictionary is actually organized in such a way that the names of the residents of a particular area are in alphabetical order, making it easier to search for a particular person. Similarly, textbook glossary will contain all the important words that have been used in the textbook, also with the page numbers where that particular word has appeared in the textbook. So if you look at these examples, a glossary can be implemented maybe using something like a hash table, and a telephone dictionary can be implemented something using like a dictionary. So different applications requires different kinds of data structures for their implementation. And choosing the right data structure for the right application is the task of this, is the goal of this course. So coming to the analysis of data structures, as I said, an algorithm is nothing but a simple set of instructions. So it's a step-by-step procedure to achieve a particular solution. So the goal of this analysis is to estimate the time required for executing these instructions. Also, we need to estimate the amount of memory consumed by these set of instructions during the process of execution. So if we just take a simple, as we all know, if we write a simple C program, the variables that we are defining, the functions that we are defining are actually consuming some memory either in the heap or the stack, depending on whether they are the global variables or local variables. So every program that we write will typically take some time to run, as well as will consume some resources in terms of memory for the execution. So these are the two parameters on which the efficiency of an algorithm is discussed. But as we all know, the memory has become cheaper and cheaper. So when we write an algorithm, our focus will be majorly on the running time of the algorithm. So what are some of the issues with respect to the practical analysis? What do I mean by practical analysis is looking at a particular algorithm and running it practically and identifying how much time it is taking to run, and also identifying how much memory is being consumed by the algorithm is what I mean by practical analysis. There are certain drawbacks when we go for a practical analysis. The running time of the algorithms are actually directly dependent on the number of inputs. That means as the number of inputs grows, the running time also increases. So practical analysis is not actually possible because of various reasons. So some of the reasons I have listed down here. So the system setup that we are choosing to run the algorithm should be same for all the inputs that we are going to test. That means the test bed that I am choosing should not be changed for the inputs. If I am running with 1000 inputs, for all the 1000 inputs, the test bed should be same. If I'm running for 10,000 inputs, for all the 10,000 inputs, the test beds would be same. Similarly, the hardware and the software configurations what we are using should be same for all the inputs. Apart from that, the actual running time of the algorithm that I am trying to test may be sometimes affected by the other processes that are actually running in the system. Because as we all know, in operating systems, the other process also consumes certain amount of CPU time and certain main memory occupation. So depending on how many processes are running and how much main memory is being consumed by those processes, the running time of the algorithm that we are trying to test will also be impacted. So, as practical analysis is not exactly possible, we go for something called as a theoretical analysis. So when we go for a theoretical analysis, an algorithm running time can be categorized into three types: best case, average case, and worst case. To understand what are these three, I'll just give an example. Like, let's say a particular marathon runner is trying to run a 5 kilometer race. So let's say the best time the marathon runner can finish off this 5 kilometer lap, maybe let's say in some 8 minutes. The same marathon runner, let's say instead of running, let's say he is just walking slowly. So he may finish the same 5 kilometer lap maybe in half an hour. And let's say the same marathon runner, instead of running at his best speed, let's say he's just doing a casual jogging. Maybe he'll cover the same 5 kilometer path in a 5 to 10 minutes. I mean, maybe 10 minutes. So here, if the marathon runner is actually putting his best effort to finish off the 5 kilometer lap, he may finish it in 6 minutes or 8 minutes, which is nothing but his best time. And the same marathon runner, when he is walking, that gives us the worst time. And when the same marathon runner, instead of running at his best speed, let's say he is doing jogging, then he may achieve the same 5 kilometer lap in average amount of time. So, given an algorithm, depending on the number of inputs that we are providing to the algorithm may run in its best time, or sometimes the algorithm may run in its worst time, or sometimes we'll go for an average case. We will discuss this best case, average case, and the worst case in the next coming lectures in detail. So, this theoretical analysis is being supported by something called as asymptotic notation. So what is asymptotic notation is nothing but it's a way to analyze the running time of an algorithm. So asymptotic notation is basically a mathematical concept which says, for suppose there is a function that will run in 3n square plus 5n time, where as n tends to infinity, the 3n square term is what is the most contributing term instead of the 5n. So I can say that the function f of n is asymptotically equivalent to the 3n square term when n tends to infinity. So more on asymptotic notation will be followed in the next lecture. So as the practical analysis is not possible, we are going for the theoretical analysis, and for theoretical analysis we are going to use asymptotic notations. Coming to the counting primitives. So counting primitives is a step where, given an algorithm, we are trying to find out how much time will be taken by each and every step that is written in the algorithm. So these are some of the primitive operations: assigning a value to a variable, performing an arithmetic operation, calling a method, comparing two numbers, indexing into an array, following an object reference, and returning from a method. So these are the primitive operations that are taken into account when we are doing the counting primitives in the next set of slides. So I've given a basic algorithm here, a findmax algorithm. This algorithm is having a curve max which is being assigned with an S of 0. Here S is nothing but an array that is storing n numbers, and the output of the algorithm will be the maximum element in the array. So like I said, the counting primitive operations are the indexing, array indexing. So when I say S of 0, it is considered as one operation because I am trying to fetch the element from S of 0 location. And once I fetch the element, I am assigning it to a Karmax variable. So assignment operation is considered as another primitive operation. So totally there are two operations in this particular statement. Similarly, 0 is assigned to I, so it is considered as one operation. Now coming to the next, while I less than n minus 1, do the following algorithm. So how many times this loop will actually run? So if you carefully observe here, the I is starting from 0. So I starts from 0 till n minus 1. So 0 to n minus 1 is nothing but n, and n plus 1th time this while condition will fail. So to be more specific, initially the I will be 0. So 0 to n minus 1 will be total n operations, and at the last iteration when I becomes n minus 1 less than n minus 1, the condition will fail. So here this condition will be checked n times, and this condition is having two primitive operations. One is an arithmetic operation n minus 1 and one is a comparison operator I less than n minus 1. So it is having two operations and this runs for n times, so totally 2n comparisons, 2n operations. When the condition is checked n times, the body of the while loop will execute n minus 1 times. I am repeating, when the condition is checked n times, the body of the while loop will execute n minus 1 times. So if you look at the if condition, here there is an array indexing operation as well as a comparison operation. So there are two operations and this will be executed n minus 1 times. So totally 2 into n minus 1 operations. Similarly, if Karmax is assigned with a of I, this is two operations. So totally 2 into n minus 1 operations. Similarly, I equal to I plus 1, or maybe I can write this as I plus plus. So here also there is an arithmetic operation and an assignment operator, so 2 into n minus 1 operations. And returning the Karmax variable, every return operation is considered as one primitive operation. So when you sum up these primitive operations, the complexity will be 8n minus 2. But if you observe in the slide, I have given that the complexity is between 6n and 8n minus 2. The reason is, when we are checking the if condition, this if condition need not necessarily be true always. If this condition fails, that indicates that this Karmax assignment with a of I, this statement will not be executed. If this statement is not getting executed, then the total number of operations will be only 6n. So that is the reason we have given that the complexity will be between 6n and 8n minus 2. How do we check the cost of the loops and the conditions? So cost is linear in terms of the number of iterations. Like I said, in the previous operation, while is a loop which is running from I is equals to 0 to n minus 1, which is costing n iterations. Nested loops, product of iteration of the loops. If outer loop has n iterations and the inner loop has m, then the cost is mn. For suppose we have written two for loops. One is I is equals to 0, I less than n, I plus plus, and that contains another for loop j is equals to 0, j less than m, j plus plus. So the cost of these two loops will be in terms of m into n. Similarly, when there are multiple loops that are not nested, the complexity is proportional to the longest running loop. For example, let's say I have written one for loop which is running only 100 times, and let's say I have written another loop which is not a nested one to the previous but a independent loop which is running around 10,000 times. So the cost of the primitive operation will be more towards the second for loop which is running 10,000 iterations. Similarly, when we go for a conditional statements like if and else, the cost of the if part or the else part, whichever is higher, that will be taken, because depending on the condition, either the if will be executed or the else will be executed. So whichever cost is maximum, that will be considered as the primitive operation. So I have given some more examples. For int I is equals to 0, I less than n, I plus plus, and sum is equals to sum plus I. So int I is equals to 0. This will be executed only once in the beginning. So this is costing one primitive operation. I less than n. I is starting from 0. 0 to n minus 1 will be total n iterations. And when I is becoming n, n less than n, the condition will fail. That means this I less than n condition will be checked totally n plus 1 times. And I plus plus will be executed only after the for loop's body got executed. So this I plus plus will be executed n times. So I have written down the same thing here. T of n is a time representation. So 1 is for I is equals to 0. I less than n is executing n plus 1 times. So I have written n plus 1 plus this I plus plus will be done only after the body of the for loop got executed. So let's look at how many times the body of the for loop gets executed. As I less than n will be successful n times, the body of the for loop gets executed n times. So n into sum is equals to sum plus I. This is an arithmetic operation and this is an assignment operation. So 1 plus 1 plus I have to do I plus plus after the body of the for loop. So I is equals to I plus 1, which contains two operations, which is 1 plus 1. So totally the time taken by this for loop to execute is 5n plus 2. Coming to the next example. Int I is equals to 0, I less than n, I plus plus. For int I j equal to 0, j less than n into n, j plus plus. Sum is equals to sum plus j. So if you carefully look at the outer for loop, I is equals to 0 will be running one time. I less than n will be running n plus 1 times, because n times it will be successful, n plus 1th time it will fail. So this will run n plus 1 times plus n, this will run for n times, because the body of the outer for loop is going to run n times. So n into whatever is written between the curly braces is actually corresponding to the inner for loop. So I plus plus is having two operations, and j is equals to 0 will run for one time. J less than n into n. So this runs n square plus 1 times. This is similar to I less than n. Here this is running n plus 1 times. Here this will run n square plus 1 times. Plus this is having two operations, and this is having two operations. So both will be n square into 2 plus 2. The total time complexity of this will be 5n cube plus 5n plus 2. I have given this example to make sure that if there are two for loops that have been given, we cannot blindly say that the time will be in something order of n square, because the number of times the for loop is getting executed will impact the running time of the loop. So here the outer for loop is running only for the n times, whereas the inner for loop is actually running for n square times. So n square into n, so the answer will be in something n cube. So if you look at the growth rates are something like this. So here on the x-axis we will have the inputs and y-axis is time. So as the inputs are increasing, the running time of the algorithm also increases. So order of 1 is a constant time, and the red one is a logarithmic time, and this is a root of n, and this is n, and this is n square, n cube, and this is exponential. So as you can see, the n indicates the linear time growth, whereas log n indicates the logarithmic time growth, and n square is the quadratic, n cube is the cubic, and n power n is the exponential time. So when we are discussing our algorithms, most of the algorithms will fall into the category of linear time or quadratic time, or in terms of the logarithmic times. So the next lecture will be on the big O notation and more into the asymptotic notations. Thank you.